Hello everyone. My name is Nagar Munir and I am a PhD student at Newcastle University. I am here to present my poster titled Robust Control of Uncertain Switch-Defined Systems via Scenario Optimization. You can scan the QR code at the top of the poster to read the archived version of the paper.
Switched affine systems are used to model complex dynamical systems with multiple modes, but uncertainties in system matrices can impact stability and performance. This paper presents a new method for designing switching control laws for these uncertain systems through data-driven scenario optimization. Instead of using relaxed invariant sets, the approach focuses on creating smaller invariant sets with quadratic Lyapunov functions, which reduces chattering effects and regulation error. The framework enhances robustness against parameter uncertainties while improving accuracy. Consider the discrete time-switched affine system, where xk is the state at time k and pi is the switching law to be designed and can change depending on the state. The matrices A, pi, and B pi are uncertain but belong respectively to the intervals underbar A, pi, overbar, A, pi, and underbar B, pi, overbar, B, pi. Introducing the error variable xi_k equal sign xk xe, the resulting error dynamics can be seen in the poster, where L_p equal sign A pi ixe plus B pi. Therefore, L pi will fall within a specific interval as you see. Here we define the concept of an invariant set of attraction. This set includes the origin, and the Lyapunov function decreases outside the set. Furthermore, if trajectories begin or reach inside the set, they remain within it. Based on these conditions, we establish the specification psi, and our goal is to design a set omega that fulfills this specification. Hence, we can define the main problem as you see in the purple box. Here you can see a high-level representation of the proposed framework. We have established error dynamics for the switched affine system. We consider the Lyapunov function as a quadratic function. Our goal is to design a switching law pi in a way that minimizes the Lyapunov function. Additionally, the invariant set omega is defined as a level set of the Lyapunov function. Keeping all of this in mind, two theorems have been developed in the paper, Theorem 4 and Theorem 6. Theorem 4 outlines the ellipsoidal set of attraction with the minimum volume. Based on this theorem, we need to solve a robust convex programming, RCP, to determine the unknown parameters and matrices of the attraction set. To establish an invariant set of attraction, we must identify additional conditions that satisfy the final criterion specified in the definition. Theorem 6 is proposed with this goal in mind, and we need to solve another RCP to find the unknown parameters of the invariant set of attraction. To address the proposed RCPs, we can use a data-driven weight and judge scenario approach proposed by Campi and Garotti in 2018. In this method, RCP1 and RCP2 can be effectively solved with a specified level of confidence by taking random samples, n and m samples respectively, from the uncertain variables. Following the weight and judge paradigm proposed by Campi and Garotti in 2018, we have the Theorem 8, which describes how to compute robustness levels with a certain confidence by identifying the number of support scenarios. Based on this theorem, the confidence level that omega satisfies specification psi is 1 minus beta 1 plus beta 2. Switched affine systems with interval uncertainty have various applications. This study focuses on two applications, MOI-MDPs and power electronic systems. Designing policies to optimize multiple objectives in IMDPs can be modeled with uncertain switched affine systems as proposed by Monir et al. In 2024 and performed through value iteration algorithms. You can see an example of an IMDP with the set of states STU, the initial state S, and the set of actions A and B. The non-zero transition probability intervals are illustrated. Here, we consider two stationary policy 1 and 2 for P, where each policy corresponds to a fixed action selection for all states and remains unchanged over time. The number of samples taken to solve scenario optimization problems is n equal to 700 and m equal to 250, with the calculated confidence being beta equal to 0.05. The results obtained via the proposed framework are illustrated in this figure. The value function evolution for IMDP is shown for lower bound matrices in A and upper bound matrices in B, with the switching law highlighted in pink. The invariant set of attraction and error trajectories for both matrices are depicted in C, while the Lyapunov function in D demonstrates that trajectories converge to and remain within the invariant set. To demonstrate our algorithm's applicability to MOIMDPs, we enhance the existing IMDP example by incorporating a second objective, resulting in an IMDP with two objectives. The number of samples in the scenario optimization problems is n equal to 1500 and m equal to 300, which gives the confidence with beta equal to 0.05. The results obtained via the proposed framework are illustrated here. The evolution of the value function for MOIMDP with lower bound matrices in A and upper bound matrices in B, including the switching law in pink. The Lyapunov function C indicates that trajectories converge to and remain within the invariant set of attraction. The class of switch-defined systems encompasses key features of various applications, including power electronic converters. Here, we applied the proposed method to single-inductor, multiple-output SIMO converter to show the effectiveness of our approach. The SIMO boost converter consists of 3 switches. Depending on the switch positions, the converter can be modeled as a switched affine system. The number of samples for scenario optimization problems are n equal 900 and m equal to 200, with confidence parameter beta equal to 0.06. The results obtained via our approach are illustrated in this figure. The evolution of states and switching laws for lower and upper bound matrices is shown in A and B. The invariant set of attraction and error trajectories are presented in C. The Lyapunov function in D indicates that trajectories converge to and stay within the attraction set. This paper introduced a novel approach for designing switching control laws in uncertain switched affine systems through data-driven scenario programming. The effectiveness of the proposed approach was demonstrated through case studies from uncertain Markov processes and power electronic systems. We were able to handle uncertainties while increasing accuracy. Future work will focus on making the scenario program robust to unseen data, improving the scalability of the approach to handle large-scale MDPs and DC microgrids, and considering time-varying Lyapunov functions to address tracking problems in microgrids.
Thank you for your attention. You can contact me via my email,